All right. So it is 3:10, so we're going to get started. I just pulled up a quick slide from a series that I help out with for professional development. So this is like part of a how to do good presentations. A couple of people were asking about significant figures or significant digits. And so I just wanted to do a quick maybe review, or for those who don't know, introduction. Okay, so who can tell me what the difference is between these things are? So 7%, 7%, 7%. What's
precision?
Yeah, so what's up there? Yeah, precision, okay. And so the basic idea is that the number of significant digits, or sig figs, denotes a level of precision, just kind of in the way that you display a number, right? And so these actually imply pretty different levels of precision. We might say 7% if you're saying like plus or minus 1%, right, versus 7.0 plus or minus 0.1%, like 7.00, indicating that I have a great deal of confidence about these two digits, about this digit, and then maybe not so much in the first one, right? So, you know, in like a econometric regression, right, if you show something like this, you are indicating something about your level of confidence in how precise these things are. Okay. Yeah, and so the way that we typically carry sig figs throughout the calculation is based on the thing that is least, the input that is least certain in your problem, right? And so if I have something like you know, I have like a 720, you know, megawatt power plant that operates, let's say, with a capacity factor of, I don't know, like 54%. Then on average, what is the power output of this plant? Who can help me out here? What's 720 times 0.54?
388.8.
388.8 megawatts. Okay, and so here, this is 4 significant digits, but these both are, well, so this is 2. This one is a little bit ambiguous when you have round numbers like this, so you could call it 2 or 3. But if we're saying 2 significant digits, right, then you're saying something like 390 megawatts. And I think that some people have a hard time saying that this is the right number when you like calculate this, right? But this is like a false level of precision based on our inputs, right? So if this was, you know, if it was 720.0 megawatts times 54.00%, that would be different, right? But here, let's say your plus or minus on your last digit, that could be, you know, anywhere between 53 to 55%, whereas this could be 54.01 down to 53.99%, right? And that would indicate like a different level of precision for this number. Does this make sense? So yeah, on the homeworks, try to do this. You know, I specify to do it in sig figs, but I'm not going to be like a huge stickler on this. I think it's just important for you guys to think about these things as you do these calculations in general. Yeah.
Do you want to assume that the trailing zeros are not significant?
Up to you. Use your judgment. I'm not going to penalize you for, you know, that assumption that you make if you've thought about it. Yeah. Okay. So that is on that piece. Okay, so before we dive in to our lecture for today, yeah, I was gone last week, so hopefully all of you guys have been able to watch the lectures. And maybe I'll just ask if there are any questions that you guys have had as you watched that material. Huh?
It's pretty straightforward.
Yeah, yeah.
One question I had was just like, how do nuclear power plants provide voltage support versus other kinds of generators?
Was I saying something specific about that in the lecture?
It was just in, you were noting just some of the characteristics of nuclear power plants.
Okay. Yeah, so I would say generally speaking with steam turbines, you have some ability, you have some ability in terms of like controlling the voltage, although a lot of, from a practical perspective, you don't need to do a lot of the adjustments out of the turbine itself. We're actually going to see here in today's lecture, like the next step of what happens to that electricity is that the voltage is going to get stepped up to do long sort of transmission. And so the voltage regulation is going to be related to the ability of the nuke to actually control some of its output. But
Okay.
yeah, I mean, I wouldn't necessarily say that's like a defining characteristic of the nuclear plant. Yeah, if that's written in the slides somewhere, I might correct that. So let me know. I'll look back at it.
Yeah, you were noting something specific about why Diablo Canyon was kept.
Ah,
But if we don't have time for it in this lecture, then
no. Okay, so that's actually slightly different. Yeah. Okay, I see. Yeah, and so I probably will be kind of making small mistakes here and there. Again, this is my first time teaching this class. With Diablo, the issue is that you are removing such a large sort of generator from like essentially from like a local generation production spot that you're going to cause lots of issues in the grid. Because like, okay, even if you have capacity throughout the rest of California to make up for what's lost in Diablo, the like local, you can, again, if we go back to our like water and pipes analogy, you can imagine like that the water pressure
helps maintain sort of the voltage of the surrounding grid.
Yes, exactly. So it's going to have such a large impact on all of the stuff that's kind of near in that area. That's something that they saw with San Onofre when it was retired. It's not just the capacity. There are like local things that happen to the grid that get affected when you pull a plant that large offline.
Isn't like, it's like frequency regulation too, because the inertia, because those turbines are so large?
Yep.
Like batteries provide like a synthetic frequency regulation?
Yeah, although I think I would describe the frequency impact of the nuke as a whole as like it provides stability in the frequency, but I would not say that it is like very responsive to
Yeah.
frequency changes because it has so much momentum.
Yeah.
So once you take something like that offline, then fluctuations in frequency are like a little bit easier, I suppose, is a way to think about it. Yeah. Okay, any other questions or things that weren't super clear from last week's recorded lectures, or anything you wanted to like talk about more, expand on? Happy to do that now. Okay. If not, we're gonna kind of continue on. And so as we dissect a lot of the grid infrastructure, right, we've started mainly sort of on the generation side. And today we're gonna talk about transmission. And so I've flashing back to this plot, right? We've got power plants kind of all across the country, but then remember, you know, where are these power plants relative to where people actually use power, right? And oftentimes, you know, if I have, you know, population centers on the coasts, right, and I have all this like power generation in the middle of the country, like how do I get the electricity from where it's produced to where it gets used? And as we talked about, right, there are lots of different types of generators throughout the country. This is kind of our rough breakdown, right? And so just to give everyone a sort of rough sense in terms of, so this is not by capacity, but this is actually by power generation, okay? As we've gone through the specifics of each individual fuel producer, here we get a perspective about how much they actually contribute into our electricity system. And so hopefully no surprise, right, as we were discussing, natural gas is kind of far and away the largest in terms of energy production. So maybe 2/5, right, of our electricity is coming from natural gas, whereas now less than 1/5 from coal. And that number, remember, as we were discussing about the sort of transition from natural gas to coal, that used to be flip-flopped or reversed. We still have a large sort of base load in nuclear, and then growing amounts from some of our renewables like wind and solar. Yeah, it used to be in the 90s, 2000s, renewable bulk coming from hydro, and it is not until sort of more recent years that we finally see wind kind of overtaking that. That was like happening even in the time that I started studying energy and electricity. And of course, right, that fuel diversity is not homogeneous across the country. You get kind of a sense of that from the map earlier, but maybe this is a little bit more explicit, and you can see the breakdown of generation types by state. Okay, so this is just like a little reference slide for you guys, if anyone's interested in seeing what that looks like. Yeah, broken down by state. Yeah, I'll also say that like grids do not operate at the state level, and so for electricity people, this is kind of a, I don't want to say a dumb slide, but it's not that useful in describing some of the attributes of the grid that people often think about. These are the geographies that we're kind of used to, but we will be breaking down and thinking about geographies in a very different way based on like grid constraints as opposed to just like state territories. Yeah.
This is in terms of what's generated per state, not exactly what's used.
Yes, I believe this is generation. To do use, it's a little bit harder. We'll talk about this well, we've actually already talked about this concept a little bit, right? But the idea that like, you know, this is just like producing water to put into the pipes. You don't actually get to know
Where it goes.
strictly where it goes. So there are ways that we can make assumptions to do attribution, but generally speaking, that would be, you'd have a lot of assumptions going into that. Yeah. Yeah, so this is going to be generally just the generation that's happening within your state. Notably, I don't think we've talked about this, but Hawaii, their biggest component is from oil. And so they basically ship in big tankers of these like big barges that drop off oil that they then burn to produce electricity. It's one of the reasons why electricity is very expensive in Hawaii, although California is now more expensive than literally shipping oil across the Pacific Ocean. But they are also very heavily pursuing renewable options to help with that particular constraint. Yes? I'll have to get back to you on that. Yeah, there's a report that I grabbed this from, but I can't recall off the top of my head. Yeah. Okay, great. And so tying back into this, right, so the question of the day is, how do we move the electricity from a giant power plant where it's produced to where we end up using it, right? So our three sort of main components of our power system: generation, transmission, distribution. We've talked about all the sort of main generation types, right, over the last 2 weeks. And today we'll be focusing just on transmission. And so transmission and distribution are both, they're kind of similar, right, in the sense that, well, generation is where I produce the power, and these two components of the grid is where I transfer the power to where it's needed. And so what is the difference? What's the fundamental difference between transmission and distribution? Any ideas?
Voltage.
Yes, it is primarily a difference in the voltage range. Okay, and so we typically are going to say transmission operates at basically a certain, once you're above a certain threshold, we basically call that transmission, okay? And so I'm going to give a rough definition of about 69 kilovolts, 69,000 volts, and above, right? So just as like a, refresher, right, qualitatively to understand voltage, right, we were describing voltage in our water analogy as kind of the pressure of the water in the pipe. So this outlet over here, I guess you guys can't see that somewhere. Well, our wall outlets, right? What is the voltage of a wall outlet? Yeah, 110 volts. And so this is, 60,000-ish times higher than that, right? And so that pressure difference is very, very large. And we'll talk about, again, why in a second. But these things are meant to transfer electricity very long distances at high volume. And we're going to talk a little bit more specifically of what comprises that sort of transmission infrastructure. Distribution is going to be operating at a lower range of voltages. So we're generally going to say something on the order of like 4 to 35,000 when we think about our primary distribution system, and then lower for our typical sort of consumer application in the secondary distribution. So 120 to 480. Yeah. 35 is maybe a little bit higher than usual, but there are places that sort of regularly operate at that sort of range. So like Southern California Edison's, who's from the LA region. Anyone? Yeah, ish, okay. So a lot of the primary distribution system in the LA region, for example, operates at 35,000 volts. Yes?
I guess two questions, but what's like the difference between the types of line layouts, like the radial line versus the other?
Yeah, so we're gonna talk about that, and that's gonna have to do with redundancy, cost, and the way that the network is laid out basically dictates the way in which electricity can like move from point A to point B. We're going to talk a lot more about interesting sort of topologies of that in the distribution system. I don't know if I cover that much in the transmission system. In the transmission system, these networks are usually like point A to point B type of things.
And then will we discuss like the difference between the primary and secondary?
Yep. So we'll talk about distribution next Thursday, because we're gonna have our guest lecture right next.
It's Tuesday. Are you talking about distribution Tuesday? Because we're talking about UC Davis Thursday and then the following Thursday.
Yeah. It's all there. It's all laid out. Yeah.
We're kind of grappling with the fact that we're going to be talking about our distribution, but you won't have talked about distribution yet.
Yeah,
We're
that's.
talking about it on Thursday, so it'll be.
Yeah.
It'll be good.
What do you know what our primary distribution operates at?
12 kV.
12 kV. Okay.
We have a little bit of 4 kV in our central heating and cooling plant, or our central cooling plant for our chillers.
Okay.
But the distribution is at 12 kV. We're interconnected to PG&E at 115 kV at the substation.
Yeah. Okay. And so that like 12 kV is a very typical, I think, voltage for like primary systems.
We're underground central campus, and overhead in west campus and south campus.
Yep.
You'll hear more about it.
Yeah. So you guys are going to hear a lot more about like specifics of as like kind of a case study, right, of the UC Davis system. Coming up soon. Okay. So we did talk about this very briefly, I think in lecture 1. Right, but the main reason why we have this difference in our transmission and distribution system is that those high voltages that we're talking about in the tens of thousands, if not hundreds of thousands of volts, help to minimize power loss over longer distances. So power loss is equal to current squared times the resistance. And so for a fixed amount of power that you're trying to transfer from point A to point B, if you increase the voltage, you can get the same power with smaller amounts of current, right? And so think of this as like a hose, right? If I have water coming out of the hose, I can increase the pressure and reduce the amount flowing through that pipe in a given moment, right, by reducing the sort of current, and the amount of water that you're going to have coming out of the hose is going to be is gonna be the same, right? And so, and conversely, you could make that pipe bigger, reduce the voltage or pressure, and have the same amount of water coming out, but you'd have more sort of passing through at any given moment. Okay, and so by doing this, you're reducing your I squared R losses because your I term goes down a lot. So resistance increases linearly with distance, and so if I just wanted to look at what that power loss would be looking like across some amount of distance, you can see if I were to go 10 kilometers with a 12 kV line, right? So our distribution level voltage line, you'd be losing, some amount of your power in comparison relative to the same amount of electricity going through higher and higher voltages, right? And so as you go up to higher voltages, your power loss will decrease. And this is just displaying what that looks like even in the distribution system, but in the transmission system, it'll be even kind of lower, right? Because our voltages are even higher. And while this increases linearly with distance, the decrease as I go to higher and higher in voltages is nonlinear because of the I square term, right? Okay, any questions about that? All right, so that's kind of the motivation for getting our voltages up to that level. And now we're going to talk about the kind of physical components of the transmission system. All right, so this kind of middle part here, there are a whole range of different voltages that are used, and we're going to explore that in just a second. We will later talk about the transmission customer, or kind of the owner of the transmission system in a later lecture. Today is more kind of about how it physically works, and then we'll talk about how it interplays in kind of the electricity market a little bit later on. And I'll touch on this piece too, because we've talked about this, but maybe not the step-up part, right? And so it's not like the electricity that comes out of the power plants that we've been talking about is right at the correct voltage that we need to send across our transmission system. And in fact, you can see what a typical voltage output out of the generator would look like depending on the fuel type, okay? So these are often producing power at voltages that are more kind of in your sort of distribution level. And so in fact, if you could get this stuff to be just located right at the location where you're consuming the power, right, you're already at your distribution voltage level. And so in theory, you might be able to, avoid some of the losses that would be happening as a result of stepping up the voltage to some of these extreme voltages for your transmission system. But those trade-offs often are not worth it, given some of these things often have like locational constraints, depending on like fuel supply lines, other attributes of these generators that might want to be like co-located next to, a river, for example. Not to mention any of the potential like externalities that you might not want next to like population centers. Okay, and so anyways, going back to this stuff, right? These are not the voltages that we want in our transmission system, and so you need a way to go from this relatively lower voltage up to the higher voltage in your transmission system. And the way they do that is with these guys. This is an example of a step-up transformer. And so what this essentially does, we're not going to get into, like I was mentioning, the physics or electrical engineering piece of this and getting into the math of like how this works. But essentially all you need to know is this transformer is going to take your low voltage and bring it up to a high voltage. Okay? So we do talk about sort of different transmission classes across that range that I was talking about. So 69 kilovolts up to 700 plus kilovolts. So sub-transmission, this is 69 kilovolts to 115. That's for like regional delivery, light transmission. Standard high voltage is 138 to 230, and that's for longer distances. And then extra high voltage, 345 to 500 kV. Those are for kind of very, very long distances. This stuff here at the bottom, ultra high voltage, this is a more modern level in our transmission classes. I don't actually think we have any built out today in the US, although I think there are plans to do that. I think the best examples of ultra high voltage lines are in China, where they are bringing in power from kind of the middle and north China, kind of down out to the coasts. These ultra high voltage lines are much, much longer distances, right? We're talking the span of, the entire country essentially. And because you're at these much higher voltages, you suffer again, kind of disproportionately less line losses. And so this is rare often because it's the sort of benefits of doing this don't get realized until you're doing these really long distance transmission. And so what do you guys think has changed recently that this is becoming like a hotter topic these days? Any ideas? Yeah.
Probably regional renewables. Like there's hydro only in the BMW, there's wind in the middle, there's solar in the south.
Yeah, wind is I think the biggest one where you don't have convenient co-location of those resources with your demand. And now that you are, you may have like saturated good wind resources near where you live. So we think about like Sweden, right, that has the big wind farm a little bit west of us. But eventually all the stuff located close to the population centers get used up. And so now we want the good stuff out in the middle of the Midwest that aren't close to population centers, and we have to transfer that really long distances. And so the like economics kind of dictate which resources get built out first. And once we've saturated that stuff, now people are more and more interested in getting to, much farther away, sort of large, plentiful wind resources, that this is starting to happen more. Okay, questions? All right, who's seen a transmission tower before? Hopefully everyone. Yes. Okay. So I'm certain if you've driven around on any major highway in the country that you've probably seen these before. So the big metal ones, that's in your transmission system, transmitted over large distances. Costs typically scale with the voltage. And with terrain, right? Building these on a flat, sort of easy to construct surfaces are going to be cheaper. But if you've got lots of hills and that sort of thing, it's going to become a lot more expensive. So in the US, and we're talking specifically about transmission, right, we've got over 600,000 miles, yeah, just in the US. Okay. I mean, this is something about the conductor cables that they use. There are some different classes of these things, right, that depend on, or that are going to be affiliated with the like voltage and the distances. Some things are going to be a little bit cheaper. Some things are going to be more expensive but more robust to higher sort of voltages. But these are essentially the things that electricity is going to travel through. Aluminum is typically a really good conductor, right? And so you want good conductors because they have low resistance, which means that you have lower power loss. Yeah, even though the voltages, we primarily think reducing current is going to do the best, you still want your resistance to be kind of as low as possible. Yeah, so conductivity, weight, corrosion, tensile strength, and obviously cost. These are kind of the set of attributes that you would want to think about as you decide on kind of the material for your conductor cables. All right. So substations. So actually, if I jump back to here. So the substation is the point at which we go from our transmission system into our distribution system. And this is going to handle a lot of the, this is essentially going to handle the step down of our voltage from these very high voltages into something that's maybe slightly more usable, right, for our end use. And the substation, oftentimes people think of breaking it down into components that are still part of the transmission system versus the distribution system, right? But this is essentially your go-between to step down to the right voltages. All right, does anyone know where the Davis substation is? For the city of Davis substation.
I know there's one on like
There's only one.
road, is it the one on Road 98? Like,
No.
Is it on L Street?
Yes. Yeah, so.
Right, like past that, and
Yeah, so if you're like on your way to Target from downtown, you know, you like turn right on L. That thing in front of you is the substation. It's got a big wall, so you can't really see into it. But yeah, that's the PG&E substation that brings in transmission level electricity and then steps it down to what all of you guys use in the city. But not on campus, right? Because the campus has a different substation, which we're gonna have a chance to visit soon.
I think our substation's actually one of our lines. I mean, to think about it this way. At least one of our lines is fed from the Davis substation.
Oh, okay. I didn't know that.
It must be transformer. Maybe it just goes through.
Yeah,
Anyway,
we'll figure that out.
see about
Yeah,
that.
yeah, interesting. There's a lot of equipment here. We're not necessarily going to go through sort of every individual component. I think we will talk about some of these elements later on, I think in the distribution lecture, and in some of the more, like when we talk about microgrid, some of the relays and circuit protectors. But generally speaking, right, the main thing is the transformer that's gonna bring our voltages down to what we need. And most of the rest of the stuff is gonna be safety equipment, right? We are operating at extremely high voltages. This is not stuff that you wanna really kind of mess around with. And so a lot of these things like circuit breakers, disconnectors, there's a lot of redundancy equipment in the substation in case anything goes wrong, right? Yeah, so basically the main thing to think about here is our sort of transformer that we need to go between our systems. Okay, any questions about this? Okay, so going back a little bit to kind of the way in which these operate. So the differences themselves within the transmission, it's not all homogeneous, as you guys are finding out, right? And so this is an example of one of the like larger transmission towers that are carrying things at very high voltages. But then you could have something like this as well, right? So this is much smaller. And so the design and implementation of your transmission system, there are many carryovers from, I guess, the way that certain entities operate, but then you are also kind of co-optimizing with like what's needed, right? And so do I need to have everything be a 500 kV line? So sure, the losses are going to be lower, but the cost might be higher. The equipment to even step up electricity and step it back down might be more expensive. And so you're thinking about a lot of these attributes of different voltages to think about what's sort of best for your system, right? And so 115 kV line, yeah, sure, your losses are going to be higher, but maybe I can use this at shorter distances. It's going to be cheaper. It's going to have a smaller footprint. I need less like protection and switching equipment to kind of step these up and down. And so economics are going to play a big role in determining like why and when I would use, I would want to have a 500 kV versus a lower voltage line.
Just out of curiosity, how dangerous is it to be beneath one of those 500 kV towers?
As far as I'm aware, there isn't really a risk with the magnetic fields to human health. It can, if you're close enough, it can mess with certain types of electrical equipment, but yeah. Not my area, so I might be wrong about that, but as far as I understand, those magnetic fields are, yeah, fine. You wouldn't want to like, if a line snapped and you had like a live wire, you don't want to be anywhere close to that, because that will literally, like at these voltages, they would literally vaporize you. There would be like absolutely nothing left. So, yeah. Yeah, there's actually, this is a total tangent, but I was just thinking about this, like being under a line. I'm pretty sure this is like a urban legend thing that physics teachers talk about. But there was, you have tremendous amounts of electricity at high voltages going through these lines, right? And so when you have electricity going through a wire like that, you have a corresponding sort of magnetic field, right? I remember my physics professor, he used to tell us the story of there was some guy some like electrical engineer who used to live under a power line, and then he would set up in his living room like a big induction coil essentially to turn that magnetic field back into electricity. And so in theory, I think in theory you could leach from the magnetic fields electricity. And then, somewhere down the line, some engineers like, oh, we're like losing electricity in this lines for some weird reason. And they would, send out someone to investigate and find out that there was this guy who was stealing electricity through the magnetic fields. I don't think that story is actually true, but, there's a interesting bit there about, who actually owns the rights to that electricity and the magnetic fields that come out of it. And I think most people would say that, yeah, the utility owns that stuff and you can't just steal it because it's like going through the air. Random tangent. Okay, so the AC/DC, we'll talk about this a little bit more. We covered some of the basics in lecture 1, right? But as a reminder, nearly all bulk electricity, with the exception of solar, produces electricity via a turbine and a generator, right? And so we talked about how, whether you're a steam generator or a gas generator, and whether that fuel is coming from coal or nuclear fission or from wind blowing through a turbine, right? The idea is that you are spinning a generator to produce electricity, and so that's going to essentially create electricity in the form of alternating current. Okay, and so with DC current, you're flowing unidirectionally, voltage is constant. This is the type of electricity that's produced from batteries and solar, and historically used over short distances, whereas AC reverses direction, so this is like oscillating sinusoidally, so we've seen that a couple times now, right? So anything where you're spinning a generator is producing AC current, and that is the standard for large-scale transmission and distribution. So why is it that we ended up with a system that mainly operates in AC on our electricity grid, right? So,
Edison shop in Hamilton?
yeah, well, there's the whole Edison-Tesla debate about whether we should be doing AC versus DC. But I think a lot of it's going to have to do with this original thing that the generation is mainly in AC. And there are other sort of benefits to this as well, right? So it's a lot easier actually to do transformation to different voltages in AC. Okay, we can use something called a passive transformer. When you have DC power, that conversion is going to be a little bit more complicated and typically more expensive. You need these things, rectifiers and inverters, right? And again, generators naturally produce AC. So let's see here. This is a nice plot that shows in red you have an AC system in your transmission, and in blue you have your cost of a transmission system that's operating in DC. And at certain voltage ranges you have AC typically being cheaper, but actually DC will catch up at some point. And so I'm gonna come back to this in a little bit. We'll talk about some of the really long distance ones. being actually operated in DC as opposed to AC. So we'll come back to this in just a second. Okay. Actually, let's see. This might be a good time to take a quick break. So let's do 5 minutes, and we'll continue at 4:05. You know, not great, but not the worst. Cold is pretty mild, so.
I hope the brain fog isn't too bad. It's one of the worst parts for me.
No, I think I can when I need to, I can just turn it on and focus. But yeah, I just try. I'm gonna totally detach after this.
Just stare at the wall for a little bit when you get back home.
Yeah.
Or listen to music
Well,
or whatever. I still
gotta.
have a kid though, huh?
Yeah, it doesn't really end with the kid.
Oh, damn.
Yeah, but that's all right. She goes to sleep. She goes to sleep at 7:30, so it's not too bad.
You can stare at your kid?
Yeah. Yes.
Oh, that might not be relaxing.
All right, 4:05. Let's continue onwards. jumping back to this, so this is a map of the transmission system in the U.S., most of the transmission system, I should say. And there's something a little interesting when you look at this map. And what do you guys, what kind of jumps out to you guys as you kind of stare at this? Anything in particular?
Super dense on the East Coast.
Yeah, so the density is generally going to kind of correspond to where like the power production is happening and where the population centers are, and so that makes a lot of kind of logical sense.
They aren't standardized.
Yeah, so tell me more about that. What do you think?
And just looking at color, you can see
Yeah.
they have different size, braided lines.
Yeah, so like when I look at the colors, there is kind of this correlation in geography, right? And so why is it that like it appears to be heavily correlated with geography, right? In California, I have a lot of yellow 230. In like Texas, in the upper part of the Midwest, I have a lot of 138 blue. And then in the like South Central Midwest area, I have a lot of 161 kilovolts in green, right? But it doesn't necessarily seem like it should be necessarily sort of so physically or geographically correlated, right? And so variation in the voltages are not so much a product of the physical constraints in those geographies, but may have more to do with like historical utility developments, with the way the philosophies of specific regional planning entities. And then they do get influenced, right, by some of those technical trade-off factors that I was talking about, where you're thinking about all these other attributes that might be tied to the economics. But yeah, a lot of it has more to do with history and philosophy. All right. So yeah, like the 138 kilovolt system was adopted very early on by utilities in Texas and the Midwest. And in comparison to like the 115 that we saw a lot in the South and on the East Coast, that was considered to be, at the time, a sort of higher voltage. And so we see a lot of that sort of prevalence in that area. So we'll talk a little bit more about sort of the regional geographies a little bit later, but ERCOT is kind of an isolated grid, and so ERCOT is essentially what we think of as the Texas grid, and it has its own sort of internal planning standards because it's isolated from the rest of the country, and so they kind of were able to do their own thing. Meanwhile, 230 kilovolts was adopted in the West, right? So you think about Pacific Gas and Electric, LADWP, as well as kind of throughout longer distances on the East Coast, where you have kind of larger load centers. This was a lot more common after the 1950s, whereas in the sort of earlier years of the grid, they're more dealing with the like 138s and 115s. WEC, which is the Western Interconnect. So that is the three main interconnects of our grid. So ERCOT, which I just mentioned. WEC is the Western Interconnect. And so that's basically everything from around here to the coast, and then you have your Eastern Interconnect, which is the rest. So WEC had a lot more explicit coordination than a lot of the other areas, which ended up leading to higher voltage standards. Yeah.
What is Nevada doing?
There's not a huge amount of like population centers out in Nevada, right? And so you got Las Vegas and Reno.
And the rest is just distribution.
Well, so there's not gonna be much distribution running from up here down to here. In fact, let me jump back to, not this guy, all the way back here. So you can see there's actually a big gap of generation kind of in the middle here. So you don't really need much transmission in this area because you don't have the population centers or the generators there. So it's kind of just that empty space for the grid at least. I'll also mention that like this is not a totally 100 complete map of the transmission system. So there's probably bits here and there that are going to be missing. Yeah, okay, and so what does this look like across the whole US? So the variation, again, as we were discussing, and then sort of the common high voltage levels across these sort of different regions. Yeah, so a lot on the West Coast is 230, even 500 in some cases. Texas, Midwest has a lot of 138, and then on the East Coast we have kind of a mix of 138, 230, and even 345. And the 345 stuff is going to be generally a little bit newer. Any questions about that? Right, and so remember that all of this stuff is operating in AC, but as I mentioned, right, in that previous slide, there are some times where the economics of doing high voltage DC transmission, when the distances are long enough, where the economics actually make sense. And you can see that happening in some places, right? A very small amount in the US, a decent bit in Europe, especially for like these long transfers across the, what is the sea that's south of Norway, Sweden, Finland? I forget what the name of that. Anyways, across that sea where there's a lot of wind resources, you do actually have some high voltage DC lines. But the bulk of it is happening right in China. And so most high voltage DC transmission that's being built right now is like super new and it's getting constructed very quickly, and it's popping up all over in China where you can transfer a lot of the like high wind resources out there to the population centers on the coast.
What's the back-to-back
I believe that's where you do like ties, where it's like two HVDC lines that connect, basically.
Huh.
I think. Let me double check that and get back to you.
So, I guess, are the economics like outweighing the physical properties there?
Yeah, you basically have these like massive resources that are located very, very far away from your population centers, and the demand for that resource is so high that it becomes worth it to build these lines. So these are a couple of the longest power transmission lines You got a couple in Brazil to connect hydro. And then in China, yeah, actually also to connect hydro to large demand sinks on the coasts. Yeah, and so these are literally thousands of miles long.
That's interesting. The turbines are hydro-powered. They make AC, right?
Yep, yeah, it's a regular old turbine and generator. And so sometimes, yeah, it's worth it to go transfer it back, transfer it into DC. Yeah, and that's all about, right, the economics and balancing, yeah, the costs against providing that particular resource. It may actually end up being more expensive to keep it in AC in some cases, right? And so efficiency, from an efficiency perspective, DC avoids reactive power losses, which is advantageous for lines at certain lengths. You get better or more precise control over power flows, which can be useful. So DC allows you to link. This is the way that we can connect grids that are not synced up. Okay, and so when I talk about WEC versus the Eastern Interconnect versus ERCOT, even though we all operate on the same frequencies, those frequencies are technically not in sync. And so you cannot just transmit power from like Colorado to like Chicago, for example, because you would cross that divide between WEC and the Eastern Interconnect. And there do exist some links between those, and that link is in DC. That's the thing that allows different frequencies to essentially connect without having to sync up. Okay, so you have to go from AC to DC back to AC.
So, by out of sync, you mean like they're out of phase?
Yes.
You can change the phase as you invert it.
No, so what I mean is that,
Or the phase, the frequency.
yeah, so our AC looks like this. Everything, you know, so this is our 60 hertz. Everything in our particular interconnect has to sync up to this. So every single spinning generator west of the Mississippi is spinning in such a way that they're essentially lined up with this frequency, right? And as you fluctuate this particular frequency, that's going to affect every generator on our electricity system slightly, right? And it might be the case, right? So if this is WEC, you know, in ERCOT, you might be slightly off sync, right? So you're not actually lined up. You cannot actually have your sort of electricity moving through the same transmission line out of sync and like adding electricity. That would actually, yeah, probably damage your generator and your power production facility. So the way that I might be able to transfer electricity from WEC into ERCOT is through a DC link.
So, how do turbines sort of maintain their sync with the grid when they're ramping up or ramping down? Like, I kind of associate ramping up as in going faster, but that would produce a higher frequency of electricity.
Yep, so basically, as you spin up there's a whole connection process to like sync up with the grid. And that whole, one of the reasons why the ramp up process takes some time, in addition to like the actual physical process of like, you know, producing steam, for example, or actually moving the turbine, is that you've got to get it in sync with your grid. There is, fortunately, some of this happens like pseudo automatically, right? The grid itself has what you might think of as like momentum. And so as you essentially connect into the grid, the actual generator will want to kind of align because of the, you can think of it as like,
Generator will start acting like a motor just a little bit, start pushing the turbine.
yeah, there's almost like a, like electrical momentum to keep you in line with what everyone else is doing. And so you will actually, if you are slightly below the frequency, and I'm saying very slightly, right, and you're connected on, you will feel pressure to essentially speed up a little bit. Yeah, this is part of where it gets tricky to like talk about this without getting into the like math and physics, but essentially the momentum of the system will force your generators to be in sync, essentially.
I have a PV system on my roof.
Yeah.
So it's, I think, modulating to, you know, when I sell electricity to the grid, it has to invert it to the right frequency of the grid, so it's monitoring the grid all the time.
Yes, and it's a little bit, well, I don't want to say easier, right? But with DC, it's a continuous output, so you can, when you do the inversion, you can choose to essentially sync up with the frequency of the grid. Yeah. Yeah. So other things, right-of-way efficiency and stability. Okay, any other questions? All right. Economics, right? So how much does this stuff cost? So the way that these things work, you typically have pretty high fixed costs, right? So think about the cost of setting up those transmission towers, and then the labor and everything associated with, string the conductors to connect to every tower. All of that is going to be fairly high cost to deploy. In addition to the economics of just the equipment, you also have to think about right-of-way acquisition, right? And so, how much does it cost to, let's say, buy or lease or get rights to, in some way, of the land in which I'm building those transmission towers? You got to go through environmental review, and then, all of the construction, as I was mentioning. So, economies of scale, large outlay, long amortization.
ROW is right of way.
Yes.
And right of way is just who built there first?
No, so when we talk about right of ways, that's usually having to do with
It's like land easements.
yeah, it's getting the you're essentially buying the ability to use the land in a certain way, right? And so, just like a transmission system, like a telecom utility would have to buy a right of way to, do optic, cable deployment, right, to bury that underground or something. Or, a gas pipeline would have to buy a right of way.
Okay, so right of way is not like a property of the electricity, but of like the physical space that
Yep.
the lines need to pass over.
Yep,
Yeah, there's
exactly.
like a famous case of Tehachapi and Chino Hills. They had all those wind farms. So
Yeah.
they were going through Chino Hills, but Chino Hills, it was an eyesore for the overhead lines.
Yeah.
So just for that, like 2 miles through Chino Hills, they had to spend like 300 million underground.
Yep. And that's a common thing, to acquire right of ways. You're going these long sort of lateral distances. Some of it is like, oh, it's like federal property, and you go to the federal government and you're able to get a right of way to build your transmission system. But then right at the edge of that, maybe you pass into a really rich or wealthy community that does not want to see these giant transmission lines and towers kind of in their community, and so they say, no, we're not going to let you do this, and you may have to spend a lot more money to like bury the ground so they're not an eyesore. So right of way acquisition sometimes can be easy, straightforward, and not that expensive, and sometimes it can skyrocket the cost of a project. Okay, low marginal cost of use, right? So once I build it, sending electricity through the line doesn't actually cost you that much money. So there's a very minimal incremental cost. And we're gonna talk a little bit more about that in a later lecture about what those incremental costs might be. But there's also these implicit costs that happen as a result of congestion. And so we're gonna spend a lot more time on this particular idea and issue, but just know that congestion on the line, in other words, a line is able to carry a certain amount of electricity, and as you send more and more electricity closer to the limit of that line, right? Suddenly you have this thing, right? That's called congestion, where I now in my transmission system have to figure out ways of transmitting my electricity from the supply to the demand, and there are these implicit costs because you're using essentially a limited resource of capacity, and that's captured in this thing called an LMP, which we're going to spend a lot more time on later. This is a locational marginal price, which helps to back out what the cost of that congestion is. Any questions about that? Yeah, so we'll spend a lot more time on LMPs in later lectures. As far as barriers, right? So the permitting and getting that right of ways might take a very long time. You have to coordinate across many jurisdictions, right? And then you might run into local opposition through NIMBYism. That's like, not in my backyard. I don't want to see this big transmission tower. And then you might have issues environmentally. Oh, are you going to be affecting the local environment in certain ways? Maybe you're planning to build this tower, but it's the site of like an endangered species or something. Yeah, so these are all barriers to getting the stuff up and running. Okay, so who pays for the transmission system at the end of the day?
We do.
That's right. And in fact, very explicitly too. So if you guys, I assume that most of you guys are on PG&E or maybe SMUD, you can break open your paper bill, or your online bill for that matter. And you can see there's, in the charges breakdown, there is a line item for transmission. And what that transmission line item is paying for is quite literally the transmission system.
Is this from your bill?
No.
Oh, okay, I was gonna say, wow, that's great. Great low bill there.
I mean, this could have been, I mean, I have, yeah, I have a solar rooftop and I'm grandfathered into an M2, so my bill might look something like this. We'll talk more about that a little bit later. But yeah, transmission, the returns are cost-based. So your return on investment for interstate lines might be something on the order of like 10% or so. Yeah, and we'll talk a little bit more about the mechanics of this later. But generally speaking, it's a rate-based recovery for utilities. So the utilities spend money to build out this infrastructure, and then that causes everyone's electricity rates to go up as they recover the investments on that transmission, and they spread out those costs to all of their customers. There are some transmission that is owned not by a utility, but by a merchant operator, but that's a little bit rarer. And this is gonna get into a whole bunch of kind of more controversial debate about cost allocation. In other words, who pays, right? And so if I have a power plant that is providing electricity to, let's say, the San Francisco area, and you're spreading out the costs of that transmission to that population in PG&E, which is like mainly in the Bay Area, we would say, okay, that seems like a pretty fair way of doing it. Now, there's also people who live up in the Sierra Nevadas out in Tahoe, right? And so I may have to build a line of the same kind of length, distance-wise, right? So let's say the power plant is, somewhere in Central California. That line might be going out to Tahoe and serving a lot less people, but the cost might be comparable, right? And so if I allocate those costs across all my customer base, well, that means that the relative amount of people benefiting from that, right, or the smaller population center in Tahoe, is essentially being cost covered by the rest of the folks in the Bay Area. And so cost allocation and who kind of pays versus who gets the benefits of this can be kind of tricky when we're thinking about the transmission system, right? At the end of the day, everyone should get the electricity, but then who pays can vary, yeah.
Is this the bill of a CCA customer? It has to be, right? Because there's a PCI charge.
Oh, yes. Yeah,
It
yeah,
has to
down
be a
here.
CCA customer.
Yeah. Yeah. We'll actually do we're gonna do a lecture on electricity rates, and we'll do a deep dive onto all the components of the bill at some point. But this is mainly just to highlight the fact that transmission is a line item bill that you guys pay for. Yeah.
What does the merchant transmission entail?
This means, so instead, it has to do with the ownership structure and the way that you charge, you cost recover. So most transmission lines are owned and operated by utilities. which are regulated in certain ways. The merchant transmission line, this is where the transmission system is actually owned by, let's say, a corporation as opposed to a utility. And the way that they choose to operate the lines and the way that in which they cost recover may be slightly different. And we're gonna have actually a whole kind of lecture on like the ownership and cost recover piece. So how much does it actually, cost physically to build these things out, right? And so obviously there's gonna be variation, right? Because it depends on things like the terrain and other sort of local conditions. But generally speaking, this is kind of your range of costs in millions of dollars per mile, okay? So, for example, the 230 kilovolt, that's what we use a lot in California. And that is operating, that's typically, the number that you typically hear is around $1 million a mile, okay? So this stuff is pretty expensive, right? And some of that like high voltage stuff can be several times more expensive. And so, yeah, you do really want to think carefully about the kind of constraints of your system and what is kind of the most economic to build out, right? And so typically the economics make the most sense generally to only move up to higher voltages as you transfer larger distances, because that's when the power losses are going to scale up. Okay? And as you can see, there is a lot of variation here. This is a plot of the line lengths versus the cost per mile. And so even in the 10 to 20 mile range, we see anywhere from as low as 150K up to 400K. And again, that does have to do with the properties of the lines and equipment themselves, but also having to do with constraints in like the construction and setting up like, building these transmission lines in like the foothills of the Sierra Nevadas is going to be very different than like setting it up in like flat Central California. Yeah.
You brought up a great point with terrain, but I guess excluding terrain, if you normalize for voltage, would you expect it to get more linear?
Yeah, you would. But I think the purposes of this is showing that besides that particular component, there are actually a lot of other things that are going to mess with your sort of total costs, right? So terrain, we mentioned, but also like the right-of-way, the easements, that's going to, on average that might be like this, but it could be a lot larger in some cases. So this is kind of a breakdown of a lot of the things that you might expect contribute to the total cost components of a transmission line. And some of these things are going to be very fairly fixed, but some of these things can have a lot of variation. Okay. Any questions about any of this? So who's been living in California, let's say non-SMUD California, for more than, let's say, 3 years? Yeah, okay. So you guys may have experienced this recently, right, which is electricity is getting really expensive. And so certainly if you've lived here for 3+ years, you've seen kind of this upward movement in electricity prices that you pay, particularly if you're in like PG&E or SCE territory. Yeah, and so this is kind of a view of that. And so, why do you guys think that is?
Underground costs for wild.
Yeah, so that's probably one of the biggest components of the cost. Yeah, this is something that we're gonna talk a little bit more in detail later on as well. But PG&E blamed for massive Northern California wildfire. Yeah, so we know that some of their equipment was responsible for starting fires and actually continues to do so, or electrical equipment, not just PG&E, but also in other places, like the Palisades fire, for example. Was early last year, that was directly attributable to the electricity infrastructure. And kind of importantly, in subsequent court cases following some of the wildfires, PG&E was actually found liable and responsible for this. And so they had to essentially pay out a whole bunch of money. And so that has kind of changed the game a little bit in the sense that they have to be responsible for damages incurred by their equipment. And as a result, one of the things that they can do to reduce probability of wildfire outcomes is to essentially bury your power lines. So we call this undergrounding. And undergrounding is definitely safer, but it's also a lot more expensive. Okay. So cost per mile to underground. So this one is particularly talking about distribution infrastructure, and you can see the cost there. And then this table here kind of describes the undergrounding costs associated with the different voltage classes in our transmission system. These are kind of approximate, but we're talking about for 230 kilovolts, our original $1 million per mile, that's now $10 million a mile, right? So 10 times more expensive. So folks have done some estimates. I mean, the utilities themselves have published reports and had to convince the Utilities Commission to do this, right? But the cost, PG&E is actually trying to underground basically their entire transmission system. And the cost to do so is going to be spread out amongst the PG&E customers. And the total cost, I've seen estimates of kind of their current transition plan, which isn't everything, but it's like 80%, I think, of the transmission lines is something like $50 billion, right? And so that deployment is one of the major contributors to why your electricity rates have kind of shot up in the recent years, because they are essentially rate basing that to their customers, and they also get a little bit of profit on top of all that, which which maybe is a contributor to their decision making. But yeah, that's probably one of the biggest reasons for spikes in our electricity rates recently. Yeah.
So you said rate basing?
Yep. So rate base is the idea that I spend a bunch of money to build infrastructure, and then I pay for that by increasing everyone's electricity rates. That's what rate basing is.
It's a fancy term.
Yeah, yeah.
Are there any other major reasons for why it's gotten more expensive?
Yeah. So, you know, in addition to this stuff, which is, you know, a very large contributor to it, California itself has generally a little bit more expensive of an electricity system when I think about it holistically, because of a lot of the push towards decarbonization and becoming a cleaner energy system. And so what's included in that? So things like much higher proportion of renewables. For a long period of time, you know, renewables may be sort of marginally more expensive than other alternative generation types. And the fact that we have requirements that X% of our electricity has to come from renewables means that we're more and more aggressively adding those renewables. Now, the cost of that capital may be sort of comparable to other generation assets like gas. But the sort of side effects of having renewables and how to deal with that also can be expensive, right? And so think about things like the duck curve, right? Where now I have to like turn on a bunch of plants at a certain time of the day very quickly. That can be expensive, and so that the like side effects of adding more and more renewables also kind of increases costs in the system. There's also a movement to electrify a lot of our end uses, which also will contribute. So we think of the positive benefits of this, like going from a gas car to an electric car, or going from a gas water heater to an electric water heater, or going from electric heating or gas heating to like a heat pump. All these things where we push end use technologies to electrify, that can increase the cost of your grid system, because now, let's say in a neighborhood, everyone's got EVs, everyone's got electric water heaters. Utility has to come in and install like a new like transformer, right? So that puts pressure on the costs to upgrade. I will caveat that by saying that a lot of times the electrification kind of pays for itself and more, which would actually do the inverse. It would actually decrease rates. But you kind of have to dig around and understand kind of how the costs are allocated to really get an accurate picture of that. Yeah.
As a follow-up to that, are they ever gonna go back down?
Yes, they are. Sorry.
Before we die?
Yes. So affordability is a huge concern right now in the California legislature and for utilities in general, because they have seen the costs kind of go up so dramatically. As I understand, they were allowed to get away with a particularly aggressive like amortization structure for the undergrounding. And so that has caused our rates to go up really quickly, but it also means that it won't be amortized for much longer periods of time that we typically experience. And so I have heard that like that the way that they've done the amortization pushes a lot of costs into the front 4 years. And so soon we should be seeing decreases in our electricity rates, as I understand, yeah.
I guess another follow-up question is, like, renewables have a lower sort of lifetime cost of electricity than a lot of the other sort of fossil fuel sources. They have a higher, or a very high capital cost, but, you know, as they continue to be used, their lack of requiring fuel makes them affordable. Is what regulating body is keeping an eye on that, making sure that the rates are going down, or that are
not increasing so fast so that you take account for the fact that like the high fraction of renewables requires less fuel?
Yeah, that is actually a fairly complicated question because that ties into the way that like some of these assets are like amortized and how they get rate based. But the simple answer to your question is the entity responsible for rates is the California Public Utilities Commission. And we're going to talk a whole lot more about PUCs and their equivalents across other states and how they regulate some of this stuff. So stay tuned, we will get to that. I feel like I've been saying that all day today. We're going to get to these things.
Good question.
Yeah, later. I promise it will come. Yeah, and after I fully kind of go through this class, you guys can give me plenty of feedback about like the organization. I try to keep it with like a lot of what we're talking about at the beginning is kind of like the infrastructure and like the equipment and what it is and how it works. But it's so hard to like just totally disentangle that from the markets and some of the like ways that it affects, you know, the economics and the rates. So I like continually touch on that, and then I just promise you guys we're going to talk a lot more about that later on. Okay, the last bit that I'm going to touch on is reliability and resilience. So what is the difference between these two? So reliability is the thing that prevents failure from happening in the first place, whereas resilience is the thing of like how you deal with a failure when it occurs. So with reliability, you want to avoid unplanned outages, and so we have this thing called N-1 security, which is just the idea that like if you lose a transmission line, like can you still make sure that everyone has electricity, right? And so they have this N-1 contingency plan at a system operator level that helps make sure that you have redundancy in your system to ensure that it's reliable. And then there are a whole bunch of metrics with which we measure that. So SAIDI and SAIFI, so System Average Interruption Duration Index and System Average Interruption Frequency Index. And so this talks about, how often am I getting certain types of like interruptions in service? How often am I getting certain interruptions and deviations in my frequency? Yeah.
Seems stupid. I thought they would have called it N+1. Since like it would be redundant to have an additional one.
Well, the way that contingency plans work is they literally do these simulations where they like cut a line. So that's the N-1.
Oh, to see how power distributes?
Yep.
Oh, okay.
Yep.
All right, that way then. That makes more sense.
And then resilience, ability to recover from and adapt to disturbances. So you have all these contingencies cases. You think about things like how long it would take to start up from like a blackout, essentially. What are the impacts of an outage, recovery rates, these sort of things. There's an entity called NERC, which is the North American Electricity Reliability Council, and they set mandatory reliability standards for planning, operations, cybersecurity, and coordination. And so they will, their requirements and standards will affect the way the transmission system is both built and operated. Yeah, so NERC reliability standards and N-1 contingency analyses that I was just mentioning. And they essentially have the transmission system is part of a broader reliability and resilience system to help maintain things like grid frequency. So you might have a drop, and then you have several levels of control. So AGCs, it's automatic generation control. This is actually related to the thing I was mentioning earlier about how you make sure the generators kind of are in sync with the electricity grid. This is one of the ways that one of the tools that they use to make sure that happens. And then you have like manual voltage and frequency management. You see like frequency is drooping. The AGC tries to get things to spin a little bit faster to keep that frequency up. And then from a secondary or tertiary level of control, an operator may say, okay, we need more, like the AGC is helping stabilize us, let's turn on a generator or force a couple generators to ramp up in a certain way to preserve things like voltage, frequency.
With like grid scale battery systems, is AGC becoming a bit more like streamlined?
Yeah, I mean, it's all part of the same system. The AGC is kind of looking at all of your assets and operating them in sync, and so batteries would certainly be like part of that equation. Yeah, so like what are the things that can go wrong? Weather, cyber attacks, physical sabotage, supply interruptions, cascading failures. And so some of these are going to affect your transmission system specifically. And so the portions of these that your transmission system is able to be resilient to, you want to think about that and build that out in a way that you can kind of weather the storm, so to say. So what are some of those things? So hardening. These are ways that you can make the equipment itself more robust. It might be like a fire-resistant design, even if it's overhead, or you do undergrounding. That is a form of hardening. So this is an example of transmission lines underground. You want redundancy, and so if you've got a demand center here and a transmission line going in here, if that's the only transmission line providing power and that goes down, you're stuck, right? But if you have two lines going in or multiple paths, that can help with like your n-1. And then microgrids and sectionalization. We'll have a bit about microgrids later on, but this is, at your distribution edge when you're at your substation going from transmission to your distribution level. The microgrid, or the way that you divide the topology, can actually make it so that when you have certain types of outages or down lines, that you'll still be able to operate essentially. So this is a little example of that. You have a line going into Winslow. This tree falls onto the transmission line, resulting in an outage to all the customers that might be getting served by this substation. But if you have a transmission that connects your substations at Murden Cove, you may create this loop, essentially, where power can travel from one substation to another and prevent that blackout in the case that this thing fails.
Like in parallel series.
Yeah, you would build out lines in parallel, essentially. Okay, so in closing, we'll say, all right, our transmission system, yeah, so this is kind of the backbone of our power system to move power from long distances with high efficiency. these are the things that are operating at the highest voltages in our electricity system. But that is complex, it requires complex planning and coordination to make all of that work. A lot of the components are chosen based on things like the performance and cost, right? But also are related to like institutional historical factors and geography. Okay. AC/DC, trade-off between flexibility, efficiency, and cost and control. Very capital intensive, slow to deploy, and is related to the way we do generation siting because that's a major constraint. Yeah, okay, and we'll leave it there for today.
Oh, 1 second.
Yes.
I should have emailed you about this beforehand, but it's mainly directed at the new students in ag. We've been spamming you guys about a